In the previous video, we saw how to create a kinematic chain and simulate the motion of a piston mechanism. In today's video, we will take it a step further. We'll perform a dynamic force analysis of this piston mechanism. What has been added compared to the previous video are these two lines at the top, which mark the top of the cylinder and the top dead center. You'll see later why these are necessary. Today, we'll mainly be dealing with dimensional constraints, as opposed to geometrical constraints, which we've already seen and used. So, how will we carry out the analysis of piston mechanism using dimensional constraints? First, we'll analyze the forces acting on the piston. That's shown here. And then the forces on the crankshaft, this triangle here. This red line is the force acting normally on the piston. Then we have the lateral wall reaction. And the resultant force, which must lie along this line here. This same resultant now appears on the other side and is broken down into normal and tangential components at the crankshaft. So it's essential first to set the geometrical constraints, and these three pairs must be coincident. This top point must be fixed so that the diagram is positioned downward from this location. Choose Fix. This component must always be vertical. We will choose Vertical and select the object. This one must always be horizontal. This force must always be parallel to the connecting rod axis. Next, we'll set a dimensional constraint for the vertical component. Select the vertical dimension from this point to this point and set it to 195. Now we'll set the parallel constraint. And there it is. With this, the triangle is fully defined. What have we achieved? If we begin simulating the piston's movement, we'll see that the forces change accordingly. The third thing we need to define is the value of 195, which represents the force on the piston. It depends on the cylinder pressure and the piston surface area, so we need to set a mathematical relation. First, we need the diameter of the piston, i.e. the cylinder bore, these dimensions here. We can set a horizontal constraint for the top edge of the cylinder. Then we fix the line representing the top of the cylinder using Fix, then Object. Next, we add two geometric constraints. From here to here. And from here to here. Why do we need them? Because we'll use these values along with the piston surface area to calculate the value of 195. Let's see how parameters are connected. You can access the parameters dialog, where you'll see all the parameters created so far. What we want to calculate is the value 195, and here's how we do it. Let's assume the pressure at the start of combustion is 30 MPa. We multiply that by D4. Then, in parenthesis, we will multiply D2, then by D2, then by pi and divide by 4. Finally, divide the result by 1000 to get the value in kilonewtons. So the force at the starting position of 23.45 millimeters is 51 kilonewtons. Now we need to analyze this triangle here. We will also apply some constraints. First, coincident between the endpoints. Then fix the bottom point. These two forces must be equal in magnitude and parallel. Also, this force must be normal to the axis. And this one parallel to it. Now the second triangle is fully defined. What's interesting here is the magnitude of this force, which will be expressed as a dimension. However, this dimension is a reference value. It's a result, not an input. It is derived based on the piston position and the formed triangle, which gives us the resulting force here. So, what's the result of this model? First, we will open the parameter manager. Now we'll modify the D3 parameter, let's say to 25. You'll see that the forces are recalculated automatically as you change the parameter. So, the greater the distance from the top of the cylinder, the smaller this force, and consequently, the smaller the component acting on the crankshaft. In the next video we will explore whether this process can be automated, specifically, creating an automatic loop that varies parameter D3 from 8 to 90 to 100 depending on the stroke length, and then plotting a force versus displacement graph based on that. So stay tuned, subscribe to our channel, and follow us to get notified when the next video goes live.